Hello everybody, welcome to session 3 in People and the Environment. This is the third of our introductory sessions. I'm calling it an introductory session because we're not so much looking at a topic within the module today as looking at an issue or a problem or an idea that underpins all the topics that we're going to be covering throughout the rest of the module. And that topic or that idea is the idea of uncertainty, specifically scientific uncertainty, and the way that that affects how people look at the outcomes of science or the recommendations of scientists in areas such as, for example, making decisions about what we can do or whether we should be doing anything about climate change. This unit comprises a SWAY presentation made up of a number of videos from different sources, with this introduction from me at the front and a number of other introductions from me. And hopefully if you work your way through this SWAY with the various resources within it, that will help you to get to grips with this really important topic. So what do we mean by uncertainty? Well, it depends who we are and the context in which we're talking to, and it should depend on who we're talking to. In everyday life, uncertainty is usually used as a measure of ignorance. How unsure about something are we? To what extent do we not know something? We think this is going to be happening, but we don't really know. Or we think this is the answer to a question, but we're not really sure. So in common usage, uncertainty is normally a bad thing. What's wrong with my car? I'm not really sure. Will this medicine help? I'm not really sure. It will be better, you think, in general usage if you could be more certain about things. In science, however, it's slightly different. It's turned around a little bit. And in science, uncertainty it's a necessary part of the process of knowing things, the process of finding things out. It's a necessary part of being clear about exactly how confident we are about something. And it's a measure sometimes of the complexity of a system. In some systems, it's inevitable that we won't ever be 100% certain about something. But we are approaching very close to that in some situations, and we need a measure of how closely we're approaching to that theoretical possibility of certainty. And so in science, uncertainty is sometimes as much a question of logic as it is a question of knowledge, and sometimes it's a question of both logic and complexity. So in the videos that follow, I'd like you to think about those different topics. The idea of knowledge, the idea of certainty, the idea of logic behind knowledge, and the idea of complexity of natural systems underpinning a degree of uncertainty in our knowledge. So common usage and scientific usage are subtly different there, and that's one of the sources of confusion when scientists talk to non-scientists. So the public understanding of scientific decisions or recommendations is hindered somewhat by this difference in usage of this important term. Now, just to try to get your head around that, try an exercise. Try making a list of things that you're really absolutely confident about, and then gradually work your way down a hierarchy towards things that you're less and less sure about. To begin with, you can do this with everyday items from your life, but gradually try to turn it around to being a list of things to do with geography, environment, people in their environment, things relevant to this topic. So, on this slide here, are you confident in Antarctica? My guess is that very few of the people in this class have actually been to Antarctica, but equally, based on having had this conversation with students previously, my guess is that there aren't many of you who actually doubt the existence of Antarctica. So what are you basing that confidence on? My guess, I say, is that I expect most of you are pretty confident that Antarctica exists. Well, what's your evidence for that? And what is your degree of certainty? Are you 100% certain? Would you bet your life on it? Or is there just a tiny little bit of uncertainty in there? Or maybe not. What about a mathematical one? What about 2 + 2 = 4? How confident are you about that? Well, in that situation, it's not so much a case of, oh, I knew someone who went there and, well, it's on all the maps, so I guess it must be true. With 2 + 2 = 4, it's a case of, well, these are the rules of maths. Here's something which operates within those rules. It matches the rules, so it must be true. So you kind of have an assumption that, well, if all the rules of maths are actually as they are, well, then 2 + 2 does equal 4. So yeah, so subject to the rules working, that is 2 + 2 = 4. So that's a matter of logic and rules, rather than a matter of, oh, someone said it, well, I've seen these examples, I've seen this evidence. So you're kind of getting two different kinds of examples there about why you may or may not be confident. One based on logic, and one based on experience or another kind of evidence. So what about the sun coming up tomorrow? How confident are you that that's going to happen? Well, that's the way the world works. The Earth is spinning. It's kind of inevitable that the sun's going to come up tomorrow morning. It's not going to come up on the other side of the planet. It's not going to suddenly start rising in the west, because that's not how the planet works. That's not how the orbit of the Earth around the sun, or the rotation of the Earth around its axis, it doesn't work in that way. So you're pretty confident about that. But asteroids, there's just a chance we might get struck by an asteroid before tomorrow, and it isn't going to happen. So you can't be maybe 100% confident. What about gravity? I mean, I'm sat here on this chair. I'm not floating off into space. Everything is sitting comfortably on the floor. If I drop something, it drops. That's being sucked down into the planet by the force of gravity. We tend to think that we're kind of pushing down onto the floor. It's not. We're being pulled down. There's this force. If I let go of that, it could just float. But no, it's being pulled down by the force of gravity. And we're used to that. It's always been there. Scientists have figured out what's going on. We're confident in gravity. If I ask you to bet when I let go of that, how confident are you? How confident are you that it's actually going to fall? We're pretty confident. We're pretty confident about exactly how fast it's going to fall as well, because we understand the rules of gravity. But suppose I ask you exactly how that's working. What is this force? What's driving that force? The more closely we look at it, there are elements of uncertainty in exactly how that mechanism is working. That uncertainty is outside of the realm of this particular module, but even in the science of gravity, there are things we don't yet know, things we don't understand. In 500 or 1,000 years, if we ask a scientist how gravity works, they'll probably give us a different answer from the answer that scientists would give us today. So there's an element of uncertainty, even in something that we can use that works every day. And what about the bouncing? When you see me, I've been doing this not terribly competently, but we can predict where this ball is going to bounce, because we know how gravity works, we know how this surface works, and I'm catching the ball each time because I can predict where it's going to go. So there's a great degree of predictability in the bounce of this ball, because I have a round ball, a flat surface, we know where it's going, we can work that out. Suppose I had a less regular surface. I'm going to do my best to bounce it vertically off that point on the top, but I only need to miss the perfect spot by a tiny bit for this to bounce off at some other angle. And dropping it from up there, I really have no confidence at all as to. I'm confident it will drop. I'm confident it'll hit the stone and it'll bounce, but it could end up over there, over here. So I'm very confident about part of this system, but then all sorts of different controlling factors are coming in to interfere with that. And the further down my system I go as to where this is eventually going to stop moving, for example, it's off in the corner somewhere. I wasn't expecting that. So the big picture we can predict with a great deal of confidence. The further we go down into the detail of the system, the less and less confident we become, because of the additional factors that are coming into play: the shape of the surface, the inaccuracy of my drop, the gradient of this table, whatever's happening off screen down here with all the rubbish on the floor that the ball is bouncing around on. So try to develop a hierarchy of confidence in that list of things that you've just made, of stuff you're very confident about, stuff you're not so confident about. What makes you more or less confident? Is it, for example, the simplicity or complexity of the system you're dealing with? That's one of the controls. Or is it a question of logic and your confidence in the rules of that logic? What is it that gives you confidence? Is it just experience? Well, it's happened 1,000 times before, it's bound to happen again. Or do you actually understand the mechanisms behind the reasons that it's happened 1,000 times before, and you know for sure that it isn't predetermined that it will happen 1,004 times and then something different will happen, because that's how the system works. What are you confident about, and why are you confident about it? And with that, excuse me for a minute while I retrieve my globe. But that experiment that we just did with my round, my globe, imagine doing that experiment again with a different kind of ball, or an odd-shaped ball. So we have an odd-shaped surface and an odd-shaped ball. And just imagine we lived in a world where gravity was different from place to place, and where we had more irregular. You could make the system more and more complicated, and the more complicated the system is, the harder it is to be confident in your predictions about the system. Now, this isn't a simple topic that, as the first time you look at it, you're going to figure it out. There are whole scientific conferences, there are whole journals, there are whole books about the idea of uncertainty and the problems that it poses, and also the constraints that it provides for how we do science. This is just a letter I got a while ago, asking me if I would be interested in submitting an abstract to a session on uncertainty in cryospheric change. And you can read through that, pause the video and read through that in your own time if you want. But basically it's saying we understand the basic idea that this is going to be happening in our physical system. We know that melting is going to happen. However, the exact timing and the exact distribution of that melting, well, there are lots of things interfering with that make it hard to be certain about the exact details. So we're not questioning that the basic thing is going to happen, we're not questioning that the ball is going to drop, we're not questioning that this melting is happening, but we're questioning the detail of how sure we can be that the ball's going to end up there, or that the melting is going to happen by this date, or that it's going to happen in this geographic region but not that geographic region. And the closer you look, the more difficult it is to make those confident predictions. Now, as I said, this is going to be a sway presentation where there are going to be a number of different videos for you to watch in addition to my introduction. You can play it how you like. If you want, you can listen to the whole of this introduction, then work your way through and look at the other videos. Or if you want to, you can pause my talk and go and look at the videos as we go through. So if you want to, there are a couple of introductory videos here about scientific uncertainty that you might want to watch at this stage, or by all means just carry on listening to me, and then these videos will crop up further down in this sway presentation. So, on the basis of what I said in the start of this introduction, and then those two videos also talk about similar issues, one of the causes of scientific uncertainty is to do with complexity in natural systems. If we had a really simple system, then we can become very confident about how parts of that system are going to work and how they're going to interact together. The more complex a natural system is, then the more potential interactions there are, and the more chance there is that a very small variation, whether the ball hits there or there, is going to make a big difference to which direction the ball bounces off. Small variations can make big differences to the outcomes in a system. There are lots of examples of this in the literature, but just using one of the articles that I've mentioned in a previous lecture, this paper by Brian Huntley is a nice example, or it's a paper that gives some nice examples of uncertainty in scientific research. So if you have a chance, you can access this through the module reading list. Go and have a look at this paper, and it's just a nice illustration of some of the uncertainty that occurs in natural systems. You don't need to read it all in great detail. I've put the abstract here, so if you want to, you can pause the video and have a look at that. But what he's talking about are these kinds of layers of complexity in natural systems that make it difficult for us to actually monitor all of the variables and to tie them together appropriately. And I've just highlighted one of the key points that he's making there, which is that most organisms aren't controlled by sort of the distribution of a tree species or where an animal species lives. Most organisms, their distribution, their behaviour, their characteristics are not controlled by a single variable. They're controlled by several variables, all operating in different ways at the same time. Now, I'm not going to dwell on the abstract as a whole. You can read that for yourselves if you want, but I just want to pull out one example to illustrate this. And this diagram shows the distribution of a particular species, but look what's controlling the northern limit to the distribution of that species and the southern limit to the distribution of the species. And you'll see that there are different things controlling the distribution of that species at its northern limit and the distribution of that species at its southern limit. That's a very simple example, but it just demonstrates that looking at one thing and understanding the temperature or the moisture question isn't going to give you the complete answer. It's the interaction of two things that you need to understand. And in reality, it's the interaction of loads of different things, giving us this complex system, which makes it harder to predict with absolute certainty exactly where things will be, when things will happen, and so on. So that was our first example, the complexity of the system. The second example of issues that underpin uncertainty that I want to mention before you move on to the other videos is the idea of the logic of scientific research. What's the logic of how we find things out? What's the logic of how we can know things? And again, just going to give you one example here, and that's the work of a philosopher of science called Karl Popper, who's been quite important in the history of geography and environmental disciplines, because he described one of the ways in which we commonly do research, which is by a process called hypothesis testing, where we come up with an idea of what the answer to our question might be, and we then say, well, let's see whether that idea, whether that possible answer is actually the right answer, or if it's the wrong answer. Can we falsify this answer? And the classic example that people use to describe what he was doing, the example that he used, was, well, suppose we're wondering what colour swans are, and we have a hypothesis that, well, we've seen swans, they're white. Well, are all swans white? And the idea was, well, how many swans would you need to see to prove that all swans were white? And if you just keep seeing more and more swans, and they're all white, you never see a swan that isn't white, you'd actually need to see every single swan in the world before you could confidently say, they're all white. But suppose you found one black swan or one non-white swan. That would be enough to falsify your hypothesis and prove that, actually, no, not all swans are white. So regardless of the truth of the matter, if you keep seeing white swans, you'll never be 100% certain that all swans are white, unless you've seen all of the swans. So even if all swans really are white, and you've seen loads of swans, and because they're all white, you have indeed only seen white swans, you can't logically be 100% certain, because there might be one that turns up that one day is different, is black. Indeed, there are black swans. So convert that to any scientific question, and you go out looking for evidence to justify, to confirm your answer, and you find that evidence. However much evidence you find supporting your answer, Popper argues you can't be sure unless you've seen every instance in every circumstance. You can never be 100% sure that you have verified or confirmed a scientific hypothesis. You can be 100% confident that you falsified it, but you can't be 100% confident that you verified it. Now, we'll talk about this in different contexts in different modules elsewhere in your course. I'm not going to dwell on it in any detail today, other than to use it just to make this point that embedded within the very nature of science, because of the logic of scientific discovery, there are situations where we cannot be 100% confident. We can be very, very, very close to that, but there's always just that element of doubt, and as a scientist we have to incorporate that in our thinking. So scientific knowledge, even, remember gravity we talked about earlier, at the moment gravity, we're not 100% sure exactly why it's working, how it's working, what's going on. There are still unanswered questions. We can predict where the ball's going to fall, Isaac Newton with his apple. But then what Newton thought turned out later on not to be quite right. His model kind of worked. You could predict where apples were going to fall, but the detail of the mechanisms behind that, we're still discovering new things. So scientific knowledge, as we call it, at any point in history, is really just a set of hypotheses that we haven't yet been able to falsify, and maybe one day we will. So even the science that we're certain about it because we haven't managed to show that it's wrong. That doesn't mean that one day we won't show that it's wrong, and the nature of science will change. And that's what science is like. So as well as having complexity as a reason behind scientific uncertainty, there's also logic as a reason behind scientific uncertainty. And scientists will be reluctant to say, yes, we're positive about this, we're 100% certain about this, even if there's no evidence to the contrary, but there's just a possibility that there might one day be. So it's very difficult to get a scientist to admit that they're certain about anything. And that is a real problem when you come to dealing with real world problems. Climate change, for example, or if you have a volcanic eruption which is being predicted and you're wondering whether to evacuate the population. There are lots of situations where the danger of saying, well, there's an element of uncertainty, is that that could be interpreted as being a statement that you don't really know what's happening. Whereas in fact, in many situations, we do know what's happening, and we know there's going to be an eruption, we know that climate is changing, but there's the 0.0001 chance that, well, there could be something that we hadn't thought about, and in a scientist's mind, that means that there's an element of uncertainty. In the general public usage of the term uncertainty, there might not be any. It's such a minuscule element of uncertainty that in common usage we'd say, no, we're certain about that, in the same way that we're certain the sun is going to rise tomorrow. There's a tiny possibility that it won't, but to all intents and purposes, we're certain. And that's the mismatch between common usage and science usage, and it becomes important in topics such as climate change, where scientists and the public are talking together. So there's a video in the Sway coming up which is all about the scientific method, and I put quote marks around the because obviously there are a variety of different scientific methods, but when you watch this video it will explain about hypothesis testing and about the idea of evidence coming together to give a weight of evidence that leads us to believe a certain thing. But it still leaves this important question about, well, even if there's a tiny bit of uncertainty, what are we going to do about actually making a decision? There's a tiny bit of uncertainty about the detail of climate change in the future. Not about climate change, but about some point of detail within it. There's a tiny bit of uncertainty about the date of this eruption or the magnitude of the eruption. We're pretty sure it's going to happen within the next 6 months, but we don't know if it's going to be tomorrow or next week, and we don't know if it's going to be massive or not so massive. So what are we going to do about that? On the practical side of decision making, this session is about scientific uncertainty and public policy, making policy for what we're going to do. Are we going to switch to electric cars? Are we going to evacuate around the volcano? What are we going to do about this? Or can we just do nothing because the scientists aren't certain? So we can just leave it for now. The scientists don't really know they aren't sure, so we don't need to act. Well, that is the fundamental problem that affects pretty much everything that we're talking about in this module. How sure do you need to be before you act? Do you need to be 100% certain? Bearing in mind that scientists don't really do 100% certain, so if you're waiting for that, you'll probably wait forever, so you'll never act. What are you going to do about that? Well, there are various possible responses, and the next video that you'll encounter as you work your way down this way talks you through one of the approaches that you might take to that. Just thinking about, well, what are you going to do? Are you going to act? Are you going to not act? What are the consequences in each situation? So have a look at that and see how that makes you feel about the decisions that you personally may have been making regarding climate change, fossil fuel use, carbon footprints, etc., etc. Finally, as we kind of move, as you move further on down towards the end of the Sway, I've put out a slightly longer talk right at the end there that just ties together some of these ideas. The videos in the Sway are all very short. They're all about 5 minutes, apart from this last one, which is 10 or 15 minutes. But it just ties together some of the issues that we'll have introduced by the time you get to that one. So have a look at that, and as always, take some notes and have a think about what's being said in that video. So by the time you've done that, you should have under your belt quite a lot of different ideas about this fundamental issue in people and environment, and the way that people react to their environment and how we make decisions in the face of necessarily uncertain science. So by the time that you've worked your way through this way, you should be up to speed with at least the basics on a variety of topics, and you should then be able to get off into your independent research and your independent reading. And what I'm particularly hoping that you'll remember as you move forward into the remainder of the course is that as you do your coursework and as you move forward into future modules, this is just a beginning point, a starting point, raising a very important issue that you need to bear in mind. Scientific uncertainty doesn't mean we don't know stuff in the same way that everyday uncertainty means that we don't know stuff, like you don't know where that, if I chuck my tennis ball over in that direction, you don't know where it is. You kind of know it's over there somewhere, but you don't know the detail. There's always going to be uncertainty. But that doesn't mean that if I say, oh, can you fetch my tennis ball please, you don't know to head off in that direction. There's a degree of certainty as well. So degrees of uncertainty are matched by corresponding degrees of certainty. And the general public view is often that uncertainty is the problem. The scientific view is often that, uncertainty just gives us a measure of the certainty which is attached to that same idea.